Institute of Engineering and Technology. Today we will discuss indeterminate forms. So let's begin with its introduction. In mathematics, several things cannot be explained by logic or by words. That things are either known as undefined or undetermined quantities, like the form 0 by 0, which is known as indeterminate forms. We know that the limit of quotient of two functions fx and gx can be written as limit x tends to a fx upon gx is equal to limit x tends to a fx upon limit x tends to a gx, provided limit x tends to a g of x not equal to 0. But if limit x tends to a gx is equal to 0, then the given result does not give any information about the limit. So let's study the indeterminate form of the type 0 by 0. If limit x tends to a f of x is equal to 0 and limit x tends to a g of x is equal to 0, then limit x tends to a fx upon gx is known as indeterminate form of the type 0 by 0. For example, limit x tends to 1, x square minus 1 upon x minus 1. So in this limit, in place of x, if you will substitute 1, so you will get the indeterminate form of the type 0 by 0. Similarly, limit x tends to 0, cos x minus 1 upon x square. So again here in place of x, if you will substitute 0, so you will get cos 0 minus 1. Now we know the answer of cos 0, that is 1. So 1 minus 1, 0, and in denominator also 0. So again we have indeterminate form of the type 0 by 0. The other indeterminate forms are infinite by infinite, 0 into infinite, infinite minus infinite, 0 raised to 0, infinite raised to 0, and 1 raised to infinite. Okay, so these are the indeterminate forms which we are going to study one by one. So firstly, let's begin with the form 0 by 0. So to solve this, we will apply L'Hopital's rule. So let's study what is the L'Hopital's rule. If fx and gx are two functions of x which can be expanded by Taylor series in the neighborhood of x is equal to a, and if limit x tends to a, f of x is equals to f of a is equal to 0, and limit x tends to a, g of x is equal to g of a is equal to 0. Okay, then limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x upon g dash x, provided g dash of a not equal to 0. Okay, so whenever if limit x tends to a, fx is 0 and limit x tends to a, gx is equal to 0. Okay, so then we have this 0 by 0 form here. Okay, so to evaluate it, what we will do, we will take derivative of numerator and denominator separately, and then we will apply the limit. Okay, so now let's begin with the proof. Using Taylor series, by assuming validity of power series expansion of fx and gx in powers of x minus a, we get limit x tends to a, f of x upon g of x is equal to limit x tends to a. Now what we will do, we will write this Taylor series of function fx in powers of x minus a. So it is f of a plus x minus a, f dash a plus x minus a whole square upon 2 factorial f double dash a, and so on. Again we will write Taylor series of function gx in powers of x minus a. So you will get g of a plus x minus a g dash a plus x minus a whole square upon 2 factorial g double dash a, and so on. Okay, now we know this limit x tends to a, f of x is equal to f of a, and that is equal to 0, and limit x tends to a, g of x is equal to g of a is equal to 0. So we will substitute 0 in f of a and g of a. So you will get limit x tends to a, x minus a, f dash a plus x minus a whole square upon 2 factorial f double dash a plus so on, and in denominator you will have x minus a into g dash a plus x minus a whole square upon 2 factorial g double dash a and so on. Now we will take x minus a common, okay, and we will cancel it. And now what remains is this. Now we will apply limits. So in place of x, everywhere we have to substitute a. So all this term will be 0 and all this term also will be 0. So what will remain is f dash a upon g dash a. Therefore we can say limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x upon g dash x. Okay. Now for our convenience, we shall use following standard limit for evaluating indeterminate forms. So the first one is limit x tends to 0 sin x upon x is equal to 1. Limit x tends to 0 tan x upon x is equal to 1. Next, limit x tends to 0 a raised to x minus 1 upon x is equal to log a, and limit x tends to 0 e raised to x minus 1 upon x is equal to log e. Now log e base is 1. Next, limit x tends to 0, 1 plus x raised to 1 upon x is equal to e, and limit x tends to infinite, 1 plus 1 upon x raised to x is equal to e. Okay, so these are the limits we will use in examples. So firstly, we will prove this limit, that is limit x tends to 0 sin x upon x is equal to 1. Okay, so what is given? That is limit x tends to 0 sin x upon x. Okay, so if you will substitute x is equal to 0 here, so you will get sin 0, that is 0, and here in denominator if you will substitute 0, so you will have 0. So we have here form 0 by 0. So we will apply L'Hopital's rule. So in L'Hopital's rule, what we have to do? We have to take derivative of numerator and denominator separately. Okay, so derivative of sin x is cos x and derivative of x is 1, right? And now if you will substitute x is equal to 0, so you will get cos 0. Okay, so cos 0 upon 1. Now we know cos 0 is 1. So the final answer is 1. So final answer of limit x tends to 0 sin x upon x is 1. This is what we have proved. Now let's evaluate one example. Limit x tends to 0 e raised to x plus e raised to minus x square minus 2 upon sin square x minus x square. So let's begin with the solution. Here we will suppose this limit as L. Okay, now if you will substitute x is equal to 0, so here you will get e raised to 0, that is 1, plus e raised to again 0, so 1, then in place of x 0, so this term is 0 and minus 2. And in denominator substitute 0, so you will get 0 minus 0. So finally you will get the form 0 by 0. Okay, so we have to apply L'Hopital's rule, right? So in L'Hopital's rule, what we have to do? We have to take derivative of numerator and denominator separately. So firstly take the derivative of numerator. So from here you will get e raised to x minus e raised to minus x. Okay, and the derivative of x square is 2x, so minus 2x. Derivative of 2, that is constant, so it is 0, upon. Now derivative of sin square x, okay, so it is 2 sin x, and we have to apply chain rule, so it is 2 sin x into cos x, right? So we can simplify it as sin 2x, right? So here write down sin 2x minus derivative of x square is 2x. Again we have to substitute x is equal to 0. So on substituting x is equal to 0, again you will get this form 0 by 0. So again we will apply L'Hopital's rule, right? So we have to take derivative of numerator and denominator separately. So on derivative you will get e raised to x plus e raised to minus x minus 2 upon, now derivative of sin 2x, that is 2 cos 2x minus derivative of 2x is minus 2. Again if you will substitute x is equal to 0 here, so you will get this form 0 by 0. So we have to apply L'Hopital's rule. So you will get limit x tends to 0 e raised to x minus e raised to minus x upon minus 4 sin 2x. Again if you will substitute x is equal to 0, you will get the form 0 by 0. Now so we have to apply L'Hopital's rule, right? So further we have to take derivative of numerator and denominator. So on derivative you will get e raised to x plus e raised to minus x upon derivative of sine 2x, that is 2 cos 2x. So here you will get minus 8 cos 2x. Now substitute x is equal to 0. So you will get e raised to 0, that is 1 plus e raised to 0. So 1 upon minus 8 cos 0. Now we know the value of cos 0, that is 1. So you will get L is equals to minus 1 upon 4. Okay, so this is our final answer. So what we have to do, we have to apply L'Hopital's rule whenever we have the form 0 by 0. Okay, until you get the finite answer. Now let's begin with another example. Limit x tends to 1, x raised to x minus x upon x minus 1 minus log x. So we will suppose this limit as L. Okay, now if you will substitute x is equal to 1, so you will get the form 0 by 0. So we will apply L'Hopital's rule, right? So we have to take derivative, right? So we know the derivative of x raised to x, that is x raised to x into 1 plus log x, and derivative of x is 1. So here we have minus 1 upon derivative of x is 1. This term is constant, so its derivative is 0, and derivative of log x is 1 upon x. Okay, now again if you will substitute x is equal to 1, you will get the form 0 by 0. So we have to apply L'Hopital's rule. So again we have to take derivative. Now to solve this derivative, we will apply u into v rule. So consider this as u and this as v. Can apply uv rule. So x raised to x as it is. Derivative of 1 plus log x, that is 1 upon x, plus 1 plus log x as it is, and derivative of x raised to x is x raised to x into 1 plus log x. This term is constant, so its derivative is 0. And derivative of this term, that is 1 is constant, so it is 0, minus as it is derivative of 1 upon x, that is minus 1 upon x square. Okay, so here you will get plus 1 upon x square. Now again if you will substitute x is equal to 1, so you will get this value. So on simplifying you will get the answer of L as 2. Now next example. Evaluate limit x tends to 0, tan square x minus x square upon x square tan square x. So let's begin with the solution. Again you have to suppose this limit as L. Okay, and in place of x substitute 0. So you will get the form 0 by 0. Now to simplify this example, what we will do, we will multiply and divide by x square. Okay, so by doing this, the sum will become easy. So what will happen is limit x tends to 0, tan square x minus x square. This x square as it is. Now we will multiply by x square and divide by x square. So you will get this term. Okay, now we know this formula, that is limit x tends to 0, tan x upon x is equal to 1. So we will use this. So this term will become 1, right? So what will remain is tan square x minus x square upon x raised to 4. Okay, now if you will substitute x is equal to 0, so you will get the form 0 by 0. So we have to apply L'Hopital's rule. So on applying L'Hopital's rule, you will get this. So firstly we have to take derivative of tan square x. So its derivative is 2 tan x into sec square x minus 2x upon 4x cube. Okay, so now in place of sec square x, what we will do, we will write 1 plus tan square x, right? So 2 tan x into 1 plus tan square x minus 2x upon 4x cube as it is. Now multiply this tan x inside, take 2 common and cancel with this 4. So you will get tan x plus tan cube x minus x upon 2x cube. So if you will substitute x is equal to 0, you will get this form 0 by 0. Okay, now so we have to apply L'Hopital's rule, right? So you will get derivative of tan x, that is x square x, plus derivative of this tan cube x, that is 3 tan square x into sec square x minus 1. Now we know this formula, that is x square x minus 1 is tan square x. So in place of sec square x minus 1, just write down tan square x plus 3 tan square x as it is upon 6x square. Okay, now take tan square x common, so you will get 1 plus 3 sec square x upon 6x square. Now we know this limit, that is limit x tends to 0, 10x upon x is equal to 1. So we will use this formula here. So this 10 square x upon this x square. Okay, so this will become 1. So what will remain is 1 plus 3 x square x upon 6. Now in place of x, if you will substitute 0 here, so you will get the answer of sec 0, that is 1. So here on numerator you will get 4 and denominator what will remain is 6. Simplify, so you will get the answer of L as 2 by 3. Okay, so I hope you have understood in this session. Thank you for watching.